Okay, question 9 of the chem bonding tutorial. We are looking at physical properties again on melting points, alright, of chlorides and fluorides of two elements. So when you take a look at magnesium, in the case of fluoride and chloride, so basically we have MgF2, MgCl2, SiF4 and SiCl4. So when we look at the boiling point, the melting point data, it's quite clear that these two have quite high melting point, and it consists of a metal and a non-metal. One look, I can presume the structure will be likely a giant ionic lattice, alright, for these two compounds. Conversely, on the case of silicon chloride and silicon fluoride, the melting points are significantly lower. So the lowest melting point, I will predict that these two, because their silicon is 214, it's somewhere in between, right? Metalloids. This will be your simple molecular structure. So which means when we're looking at melting, we're looking at IMF, intermolecular forces, whereas for MgF2, MgCl2, we're looking at your ionic bonds. Okay? And this will give you some indication in terms of the relative melting points. Okay, so for MgCl2 and SiCl4, MgCl2, we just say it's a giant ionic lattice, whereas for SiCl4 will be your simple molecular. Okay, for SiCl4, we need to identify the type of IMF. So for these two compounds, silicon is group 14, so you need 4 bonds to achieve contact. So just quickly, let's do one example. You can just basically replace the F with all the C's as well. Alright, so you have 4 bond pairs, 0 lone pairs around the silicon, tetrahedral in shape. So we draw a 3-dimensional. So this is going to be non-polar. Why? Because the dipole moments cancels out each other. Alright, so no net dipole. So type of IMF will actually be your ID. Okay? So MgCl2 and SiCl4, let's analyze. In this case, we state the structure up front, giant ionic structure, SiCl4, simple molecular structure. Type of bonds that we're overcoming when we are doing melting for giant ionic will be strong ionic bonds. Okay, so giant ionic lattice, during melting, ionic bonds. Okay, between oppositely charged ions. So remember, when we talk about bonding, we have to state the particles. As compared to the IMF. What's the IMF in this case? Your weak intermolecular ID between your molecules. Okay? So you can see direct comparison. And that's why you can see that's a big difference in terms of the melting point. Okay? Moving on to SiF4 and SiCl4. So in this case, we earlier analyzed these are both simple molecular, and both of them are non-polar, which means they only have an ID. So recall, why is there a difference in the melting point? Why is silicon chloride having a higher melting point than that of silicon fluoride? So since they only have non-polar, it's going to be ID. Think about the factors that affect the strength of ID. One, do they have comparable MR? Alright, no, because chlorine is below fluorine in the periodic table. Alright, as a result, the electron cloud size becomes a discriminating factor. So in this case, again, same thing, I talk about the structure, simple molecular structure. And I zoom in straight away to the one that distinguishes them, which is the size of electron cloud. Okay, because if you calculate the MR of SiCl4, it's going to be bigger and that of MR of SiF4. And this is implications of the electron cloud size. We know that the electron cloud size is bigger, the distortion of the electron cloud will be more significant. And this leads to greater extent of IDID. And once we have more extensive IDID, the energy requirement will be higher for SiCl4 to overcome the weak IDID. Okay, last part for C for magnesium fluoride and magnesium chloride. These are both your giant ionic lattice structure. Okay, so recall what we discussed in the earlier question when we compared ionic bonds in question 2 of the tutorial. To compare ionic bonds strength, we look at this formula, right? Lattice energy. And this formula should be something that's quite familiar to most of you. Q plus Q minus over R plus R minus. Alright, a charge of ions and anions. In this case, analysis Mg2 plus is the same. The only difference is the F minus versus the Cl minus. Charge is also the same. So largely I'm looking at the concept of R minus, the radius of the anion. So in this case, you can see how I phrase my answer. Since cation is the same, I just say cation charge and the radius are the same. Anionic radius, anionic charge is the same, not the radius. Okay, the radius is the one that changes. Chloride is bigger than fluoride. And what implication does it have for the magnetic or lattice energy? So if the radius of your anion is bigger, your lattice energy magnitude will be smaller. So if this one is bigger, your lattice energy magnitude will be smaller. So MgCl2 will have a smaller lattice energy magnitude. So if lattice energy is smaller, it means the ionic bonds are weaker. Alright, because we say lattice energy is a measure of the strength of ionic bonds. Alright, so we look at energy requirement to overcome the ionic bonds. If you have charged ions, MgCl2 will require less energy, and that's why melting point of MgCl2 will be lower than that of MgF2. Okay, with that, we're done with question 9.